good morning physics class. Welcome to Thursday, June the 4th. And before we get started today with our topic today, which is on satellites of Earth, I want to go back and cover one of the questions on yesterday's assignment, question number 5. And before we do that, I want to share with you a verse of the day again today. And so today comes from Psalm chapter 8, and we are going to read verses 1, 3, and 4. All right, so here we go. It says, O Lord, our Lord, how majestic is your name in all the earth. You have set your glory above the heavens. When I consider your heavens, the work of your fingers, the moon and the stars, which you have set in place, what is man that you are mindful of him, the Son of Man that you cared for him? So there we go again. God setting the stars and the moon and the sun in place, and but still, as great and glorious as he is, he cares for us and loves us. All right, as we look at question 5, now before we look at question 5 specifically, I want to share with you something that I didn't tell you yesterday purposely, just to see if you could figure this out sort of on your own a little bit. And I'm guessing it's challenging. I don't know if any of you did it or not. Feel free to let me know. But yesterday we developed this formula here that Fg equals g, the gravitational constant, times m1, m2 over d squared. All right, so we learned that yesterday. Way back in grade 11, and we used it a little bit this year already as well, we learned that Fg equals m times g. Now this is the force of gravity on Earth. This is the universal force of gravity. They should equal one another, right? This is the gravitational force between any two objects, which would include you and me standing on the Earth. So the force of gravity between you and the Earth, or me and the Earth, right? So, and this is the force of gravity of a person on Earth, or on any planet for that matter, okay? But G changes, right? So what we want to do is we want to show that these two do in fact equal. Now we know that the gravitational field constant on Earth is 9.8 newtons per kilogram. All right, so if I make these equal to each other, right? So mg, the force of gravity as we previously have seen it, equaling the universal gravitational law, right? Now what we have to realize here is that in the gravitational field, this is the force of gravity between two objects. So one of them is the Earth and one of them is us. Right? Over here, this force of gravity is the force of gravity on us, which means the mass, m, one of these masses, is the same, right? This mass is the same as one of these masses, and the other mass would be the mass of the Earth. All right, so that leaves us with g, lowercase g, the gravitational field constant for Earth, equaling the gravitational field constant, the universal gravitational field constant, mass of the Earth over the distance squared between us and the Earth. Now you might think, well, there is no distance between us and the Earth because we're standing on the Earth. When we do distances, we always do it from the middle of the object. All right, so from the middle of the Earth to us, which is otherwise known as the radius of the Earth. Okay, so the distance here will be the radius of the Earth. All right, going to our chart that I gave you, the solar system data chart. Again, we know that G is 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared, not squared, times the mass of the Earth, which is in your chart, 5.98 times 10 to the 24 kilograms, divided by the radius of the Earth, 6.38 times 10 to the 6 meters squared. If we multiply this out, we will get 9.8 newtons per kilogram. So it works for Earth. Now it works for any planet. In the question that you were doing, I'll just find it here real quick. The question asked you to find the gravitational field constant on Jupiter. Well, the only thing that changes here is that instead of using the mass of Earth, we're going to use the mass of Jupiter. Right? Nothing else changes. Because on any planet, it's the force of gravity equals mass times the gravitational field constant. On any planet, anywhere in the universe, the force of gravity is equal to g m1 m2 over d squared. can always be this, okay, where again, one of the masses is going to cancel out because that's the mass of the object that's on the planet. So again, you or me if we're standing on a planet, right? And then we can again solve for lowercase g, the gravitational field constant on Jupiter. And gravitational field constants and the acceleration due to gravity are always both equal to the same number. All right, so the only thing that changes here is the data. Instead of using Earth's data, we're going to use Jupiter's data. Go back to the chart that I gave you. Jupiter has a mass of 1.9 times 10 to the 27. And so it's heavier than the Earth, and it has a radius of 7.18 times 10 to the 7. And again, significantly larger than the Earth. And if we plug that into our calculators, we will get the correct answer, which I believe was 24 point something. 24 meters per second. So this would be 24 newtons per kilogram, but a newton per kilogram equals a meter per second squared. All right, and again, there's some unit analysis that we can do there. A newton is mass times acceleration, so kilogram, meter per second, and then with per kilogram, the kilograms cancel out, leaving us with meters per second. All right, so that's how you do question 5. Again, remembering that the universal force of gravity and the force of gravity on a planet have to equal each other. This wouldn't be universal if they didn't equal each other. All right, so has to equal, and it's a way for us to find the acceleration due to gravity on various planets. All right, let's go talk about satellites of Earth. All right, as we start looking at satellites of Earth, now we all have seen satellites in the past. We have a concept of them. A simple satellite of Earth is the moon, but there are literally thousands of other satellites that are orbiting Earth at any given time. So yeah, we see them from time to time. If you look up at the night sky, sometimes you can see what looks like a star moving really quickly across the sky. Probably some kind of satellite, right? We use satellites for TV, for our cell service, for internet service, for all kinds of things. We're using satellites, and a whole bunch of various companies have their own satellites orbiting the Earth in a variety of different ways. The International Space Station is also a satellite of Earth. It is orbiting Earth as it does its scientific experiments out there. All right, so as we think of a satellite orbiting Earth, and again, it's not a circular path, but it's close enough to a circular path that we can use our circular motion. So here we have the Earth, and we have a satellite that is going to be traveling around the Earth in a circular pattern. And so from the center of the Earth to that satellite is the radius of the circle. Now, if we think back to our centripetal motion unit, okay, a centripetal force was the force that is keeping the object in its circular motion. So if you think from the satellite's perspective here, what force is keeping it traveling in a circular motion? Well, it's the force of gravity. So knowing that, the centripetal force, which again is a net force, is equal to the force of gravity. Right, because again, centripetal force is the force, the net force that is keeping the object in its circular path. In this case, that's gravity. Over here, I've written down as a reminder our 3 centripetal force formulas. Okay, and we can use any one of these depending on, again, what information we have, what information we want to find. All right, so we'll do a couple questions today. One of the things that we do know, though, is if we're using this formula in the middle here, the 4 pi squared mrt squared, we know the t here is the period of revolution, and we know the period of revolution of many of the things that go around the Earth, right? For instance, the moon takes 27 days, 27.2 days to be exact, to travel around the Earth. And we know that because we can observe it and we can watch it. Right, there's many other things that we know the period of revolution around the Earth. So we know that one. So we're going to be using this one more frequently than we'll use the frequency, because frequency, again, is a different quantity that takes a bit of calculating to do. All right, so here's our formula. Again, let's say we were using the period one. We would do 4 pi squared mr over t squared would then equal to g m1 m2 over d squared. Now here's where you have to remember and be careful. You see we have an r on this side and a d on this side. Well, this r is the radius of the circle, right? This d is the distance between the two objects. They are one and the same, all right? So r equals to d, which means that when you're doing this, to make your life simpler, you're going to want to change the d to an r. And whether it's uppercase r or lowercase r doesn't matter. You'll see it both ways depending on which textbook I give you questions out of. All right, but it's important to remember that while the r in the centripetal force one stands for radius, and the d in the universal gravitation equation stands for the distance between the two objects, in a case where we have an object revolving around another, they are the same number. And so we're going to want to make it the same variable, so when we collect our like terms, it makes sense. All right, we're going to give you 2 examples. Now we're going to go solve 2 examples, one on the other board, and that'll be it for today, and then you'll get a short assignment that deals with some of this stuff. So let's go do a quick example. Okay, so here's our example. We have calculate the speed required for a satellite to remain in a circular orbit 100 kilometers above the Earth's surface. So we're going to start with a couple pieces of information here. The first thing we're going to recognize again is that it's in a circular motion, and the force that's keeping it in its circular motion is the force of gravity. So we're going to start with that. We want to find velocity. So our centripetal force has to be the one that has velocity in it. So mv squared over r. And I just realized on the other board, I forgot the mass in our formula for centripetal force. All right, centripetal force is mass times v squared over r. So if you go back and watch the last 30 seconds of the video over there and you see the formulas on the board in the box in the corner, the top formula for centripetal force was wrong. It was missing the mass. It should have said Fc equals mv squared over r. All right, the other side is right though. We're going to go g m1 m2 over d squared. And again, you're going to recognize that this r is the radius between the two objects, and this d is the distance between the two objects, and so they are one and the same. So again, I'm going to change this to an r squared. Now, here's where you got to be a little careful. R here is not just the radius of the Earth, right? We have the Earth, and then we have the satellite 100 kilometers above the Earth, right? So our radius, or the distance between them, is going to be the 6.38 times 10 to the 6 meters, right, for the radius of the Earth, plus 100 kilometers. Okay, we're going to change these units appropriately, but what you're going to get is you're going to get 6.39 times 10 to the, right, times 10 to the 6 meters. All right, so this is going to be the R we're going to use. Okay, now remember, you're not just adding 100 to this, right? This is 100 kilometers, and this is in meters, so make sure you're adding the right number. All right, now we're ready to go. Now we know that this is the mass of the satellite, this is the mass of the Earth, this is the mass of the satellite, and so the mass of the satellites cancel out, leaving us with v squared over r equals g mass of the Earth over r squared. We can continue to simplify by multiplying this r into the numerator and taking the square root. It's going to give us v equals the square root of g times the mass of the Earth over r. Right, when I multiply this r up top here, it's going to cancel with one of those. All right, so this becomes the formula. Let's fill in our numbers because we know them. G is 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared times the mass of the Earth, 5.98 times 10 to the 24, divided by the radius, which we found earlier here, is 6.39 times 10 to the 6 meters. Plug that into your calculator and you will get a velocity of 7.9 times 10 to the 3 meters per second. Okay. There you go. That is how fast the satellite will have to be traveling to remain in a circular orbit 100 kilometers above the surface of the Earth. All right, there you have it. Let's go do one more example, and then I'll give you your assignment. All right, here's our last example. What is the height above the Earth's surface of a geosynchronous satellite? So first question you have to answer to yourself is, what is a geosynchronous satellite? Geosynchronous means synchronized with the Earth. So what that means is that as the Earth rotates, the satellite is rotating at the same place, which means the satellite is staying above the same place on Earth at all times. Hey, it is synchronized with the Earth, geosynchronous. All right, so it would appear that there's not a lot of information given in this question, but in fact we do have a lot of information. Again, we're going to recognize that the centripetal force, the force that is keeping this satellite in orbit, is the force of gravity. All right, now the fact that it's geosynchronous gives us a period, it gives us a time for one revolution, right? Because we all know, I hope we all know, how long it takes the Earth to rotate once on its axis. I hope you all know that the period of rotation for the Earth is 24 hours. And you convert that into seconds, which is what we're going to need to do. We need to have our time in seconds. Because we have newtons, and in our equation, like G, the constant is 6.67 newtons meters squared per kilogram squared, and then Newton has a meter per second in it, so it has to be seconds. So converting it to seconds, we get 8.61 times 10 to the 4, I believe, 4 seconds, times 10 to the 4 seconds. All right, so that's our period of rotation. So now we know the period of rotation. We want to find the height. We want to find D or R, and we know the masses that we need to know. All right, so over here we're going to go FC is going to equal our 4 pi squared m r over t squared. This side is G m1 m2 over, and I'm already going to make this r squared. Okay. Again, one of these masses, this mass, cancels with one of these, and this means it's the satellite mass cancels out, and it is the mass of the Earth that we're going to use. And now we want to solve for r. All right, so what's going to happen is we're going to multiply r squared to both sides, which is going to give us r cubed. We're going to take this t squared and multiply it to the numerator. So g m1 times t squared, and this 4 pi squared gets divided on both sides, leaving us with this. And then of course we'll get the answer and we'll take the cube root. All right, so let's plug in some numbers here. We know that g, 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. Mass of the Earth, 5.98 times 10 to the 24 kilograms. Time is this 8.61 times 10 to the 4 seconds squared over 4 pi squared. And then of course, to get r, you're going to take the cube root of that. Okay? Like that. And what that will give you is that will give us an R that is equal to 4.22 times 10 to the 7 meters. And now you might think you're done. You might think that's the answer, but in fact it is not. We draw a little diagram here. What we have here is we have the Earth, we have our satellite. The distance from the center of the Earth to the center of the satellite is the number we just found. Okay, but that's not the height above the Earth, because the height above the Earth is only this section here, which is going to be this number minus the radius of the Earth. So I'll do this over here. We're going to go height will equal to the 4.22 times 10 to the 7 meters minus the radius of the Earth, 6.38 times 10 to the 6 meters, and our height above the Earth will equal to 3.58 times 10 to the 7 meters. And so that number there becomes the height above the Earth's surface. Okay, but again, it all comes down to every question we've done started with FC equals FG. FC has 3 different formulas that we can use depending on what we're given or what we want to find. In the previous example, we wanted velocity, so we used mv squared over r. In this question, we wanted to find a radius given a period, and so we used the 4 pi squared mr over t squared formula. All right, so but it all starts the same way. Put in the appropriate numbers, do a little bit of algebra to solve for your final answer, for the answer, and then make sure you're getting the answer that the question's looking for. All right, you will find a short assignment on Connect, a photocopied thing out of your textbook, and that'll be it for today. So have a great day, and we will see you tomorrow.